Hello, 1332 students. This is about section 2.4, talking about Venn diagrams, and even when you're dealing with a universal set that has three subsets, how a Venn diagram can help you organize and quickly answer questions like, for example, the following. So, here's a universal set, all the numbers from 1 to 12, all the natural numbers. Here's set A, set B, set C, all subsets of the universal set. And let's say you're asked to find a bunch of manipulations of all those set operations, union, intersection, with parentheses. So remember, it's like PEMDAS, whatever is going on inside the parentheses is meant to be evaluated first, and complementation. So if you were just going to try and do this problem from, just using roster method of sets, this would take you quite a while. You'd have to break it up into many little parts, okay? Whereas if you use a Venn diagram to organize your work, a lot of things are a lot easier to answer. So for example, so first of all, I took that universal set and the descriptions over there of each of the subsets A, B, and C, and made a Venn diagram with three subsets A, B, and C, and put the elements in the right places. Okay, once you have this tool, then a question like this one, find the intersection of the complement of A intersect B with C. It's a lot easier to do. So remember, if you remember the tricks about how to find a complement and so forth, using a Venn diagram. So A intersection B draws your eye to that little almond-like sliver right there. And if you want its complement, you just cover up what's inside that sliver. So the complement of A intersection B is everything visible now, right? So in other words, everything in that universe except for the number 3. So this part right here is everything except for the number 3. But that's not what they're asking for. They're asking for, if you take the complement of A intersection C, which now we're looking at without writing anything down, and say, what of all those elements that are visible, which ones are also just in C? So that would be 8, 1, 9, 5, and 12. So just by putting one pen down, you can answer what that set is. This is the beauty of the Venn diagram. Okay, here's another one. The second question was asking for something like this: A intersection B intersection C, which is that little trefoil-like shape in the middle, which in this example we can see, oh, that's empty. Now we can see it, right? But the question, number 2 over there, was find all this, right? But if A intersection B intersection C is clearly the empty set, right, because it's right in front of you there, there's nothing in there, okay? And since we have a rule that the empty set union any set is just the set itself, right? Union means of two sets, you take anything that's in that set, pour it in the bowl, take anything that's that set, pour it in the bowl. What's in the bowl? Well, there was nothing in this one. All the contributions came from S, so their union is just S. That's true for any set. So if I use that here, if this is just the empty set, union this other set, well, that just reduces to that set, B intersection A complement. Well, what does that look like? Okay, so A complement, let's think about what that is. Back up to the picture. A complement, well, just put your hand over A. What you're looking at, what's left, is A complement. Of all those things in A complement, what is in B? 7, 1, and 9. And so you just write that down. So it's a lot less of writing things, not quite so many layers than if you had tried to do those 2 questions just from looking at sets and writing more sets in roster method. The third question was to find A intersection B union B intersection C, union A intersection C. Well, let's look at this piecemeal, right? Those parentheses are telling us to evaluate those three things first. What's A intersection B? That's the stuff in here. B intersection C, that's the stuff in that sliver there, that sort of almond-like shape. What's in A intersection C? Everything in here. So, so for each one of those, I wrote down what they were. And now I look at these operations in between. That's a union. Okay, so just take everything that's in this set, throw it in the bowl, everything in this set, throw it in the bowl, just throw them all in. That's what's in the union. That's way faster than if we had tried to do it without a Venn diagram. All right, so part 2 of this lecture on section 2.4, I wanted to point out that DeMorgan's laws don't go away. Remember, we talked about this in previous videos, and it's also in your book, in the reading of the book, that the complement of the union of two sets is equal to the intersection of their complements, and that the complement of the intersection is equal to the union of the complements. So remember, the way to sort of think about it notationally is that when you're taking a complement of a union, it's like you're distributing the complement through there. Everything gets hit by the complement. The A, the B, and even the union gets reversed into an intersection. And same thing down here. You just sort of distribute that complement, and you get A complement, B complement, and instead of an intersection, now you have a union. That makes it easy to memorize. And of course, you can keep using that even if there's more than just two sets floating around. So for example, let's say you were tasked with finding this set here. The intersection of A complement, B complement, union the intersection of B complement, C complement, right? So one application of DeMorgan's law says this is equal to that, right? So the analogy here is that we're kind of factoring out the prime, factoring out the complement. So just undo everything. This A complement becomes an A, the B complement becomes a B, and the intersection becomes a union. But put that complement sign out there outside of the parentheses. Okay, so that's one application of DeMorgan's there. Here's another. This, if I apply DeMorgan's laws to it, becomes B union C, the entire quantity's complement. All right? But look what we have here. We have a negation, the complement of something, union the complement of something. The complement of something, union the complement of something. According to DeMorgan's laws, you could take a complement all the way out there and just affect all three symbols. So going from here to there, I have taken off the complement on A union B. From here to here, I have taken off the complement on B union C. I have turned this union into an intersection. It's all good. This line equals that line as long as I'm taking the complement on the outside of that whole structure. Now, how do I know, assuming, by the way, I'm using the same Venn diagram as before, the same universal sets and the sets A, B, and C that we defined in the first part, how do I know it's equal to that? Well, this is where the Venn diagrams help quite a bit. So if we go back to the Venn diagram that we had in the first part of this 2.4 video, get you closer. Right. So 2, that's too close. All right, so you should be able to see all the way down to here. Yes, okay, good. Okay, so there's that same universal set with A, B, and C, and these numbers 1 through 12 distributed as in the first part of the video. Okay. Now, look how, after using DeMorgan's law, what do we need to find? We need to find A union B, And here I'm demonstrating the use of shading. Okay, so you can shade the parts, the regions of that universal set that make up A union B. Your book can't use shading as easily as, well, nobody can use shading easily. This takes a while to construct. Your book would say these are regions 1, 2, and 3, 4, 5, and 6 are in A union B. And B union C, what is it? Well, it's, excuse me, that's missing a little bit of red there. It's everything in either B or C, right? Your book would call this regions 2, 3, 4, 5, 6, and 7. That's B union C. Now, what is in the intersection of these two sets? A way of thinking of it is, what are the set of all regions that get painted twice? Well, let's see. You'll notice the trefoil in the interior and these 3 petals, they are being used in both situations. So all 3 of those branches, oops, that should be blue. All 3 of those branches and the trefoil in the middle should be included. So when I'm saying branches and trefoils, what am I talking about? I'm talking about region 2, 4, 5, and 6. They're all in there. What else gets painted in both pictures, right? We want the intersection. Well, this part of B that's outside of the intersection of any of the other sets, that is painted in both, so it's painted in the intersection. And so now we have that the intersection of A union B and B union C looks like this. So what is its complement? Well, the complement is everything outside of the blue region. I'm modifying my answer right here. That was blue, and it's going to stay blue. So what's the complement? Now I've gone back and filled in the elements that were sitting in this region, in that region, and out here. So it should be, going back over to the answer, writing it in roster form with one slight correction. Can you see what I should be correcting? Let me stand over here so I don't put a shadow on it. What's in the complement of that set? 2, 4, 5, 12, 6, 10, 11. So I have 2, 3. Let me get rid of that 3. And now we're good. Okay? So the Venn diagram, along with DeMorgan's laws of complementation, can help you get through some of the nastier looking sets you're trying to find.